Who actually knows who I am? About less than half of you. Okay, so to the benefit of those who lived in blissful ignorance all this time, my name is Francis Livens, and I wear various hats in this school and around the university. I'm formerly the Professor of Radiochemistry. I have a long-standing interest in things environmental, and that has given the school sufficient excuse to ask me to teach these lectures to you. My apologies for cancelling last week. I had something which was an invitation I couldn't refuse. So we're starting a week late, but there's enough slack in the programme that we'll catch it up. Some of you may well know some of this stuff, particularly the earlier material, if you've done things like geography or geology somewhere along the way. What I would ask you, please, is don't feel that you can not turn up, because there are some little twists to it, there are some slants to it that I'll give, and you may think that you know what you need to know, but actually you might just get an unpleasant surprise. All the slides are on Blackboard, so you can have a look at those. Again, that includes all the slides for future lectures, but please don't think that just because you can download all the slides from Blackboard, you can lie your pit for the next 11 weeks on a Thursday morning. No, not this Monday morning. It's been a funny week. You'll need a handout. So you. So that's a little bit of a preamble. I always struggle a little bit with the title for this course, though currently it's called Introduction to Earth's Processes. And what we're really interested in is understanding a little bit about how the Earth works as a planet, and then particularly how near-surface... Mobile's off, keys or silent, thank you. How the processes that operate on the surface of the Earth affect the behaviour of trace elements. And we'll pick some examples as we go along. I've stolen this from a next door lecture theatre, so I'm not jumping up and down with a big stick anymore. I've gone technological with a green laser. That's my email. I do read them, and I do my very, very best to respond. So please drop me an email if you've any particular queries. So I'm going to start by introducing the idea of biogeochemical cycles. Because that's a useful framework for understanding how the processes that we're interested in actually move material around. I'll then go on and start to talk about what I call the Earth as a planet. So that is the deep structure of the Earth, the history of the planet's evolution, and all that in about 20 minutes. And then we'll move on to the building blocks of the solid Earth, which are rocks and minerals. Now you might think you know what a rock is and what a mineral is, but there's a little bit of subtlety there, and for people who are used to thinking of things as chemists think of them, then actually rocks and minerals are dangerously heterogeneous. So it's understanding how conventional inorganic chemistry relates a bit to rocks and minerals. Then we start to think quite specifically about near-surface processes, so that takes us into weathering and alteration. How do things respond physically and chemically to finding themselves on the surface of the Earth when actually they're thermodynamically stable in very different conditions? Weathering and alteration lead us to secondary minerals. In most places on the Earth's surface you find at least some organic matter, mixed up with primary and secondary minerals, and all that lot together is a soil, or if it's in water, it's a sediment. So we'll talk about soils and sediments. Then about geochemical parameters that are really important in understanding trace element mobility. So that's particularly pH and the redox status. And we'll have a little excursion through freshwater chemistry. We'll look a little bit at some of the influences of biological processes, because the Earth's surface is by and large biologically active. And then we'll finish by trying to tie together all these different ideas in a case study of one particular place, an old copper mine in northeast Anglesey, a place called Paris Mountain. So that's the plan, and that will take us the next 11 lectures. Probably won't if we get lucky. So there's a bit of terminology to use here when we're starting to talk about biogeochemical cycles. And helpfully, I've defined the first, or in the first definition, I've used a term that's defined later on. So a source is simply some part of a biogeochemical cycle. We'll look at an example in a moment, where the amount of whatever we're interested in flowing out of it is greater than the amount flowing into it. Well, I've done it the other way around. Inflows less than outflows. The flux is the rate of transfer. So that's the rate at which you're moving material. And the net flux is the difference, for any component, is the difference between what's coming in, the rate at which stuff comes in and the rate at which stuff goes out. A sink is the reverse of a source. A sink is a component where outflows are less than inflows. In other words, whatever you're following around this cycle accumulates in sinks. And component can be very broadly defined. It's just a part of a biogeochemical cycle. You might choose to define it physically by virtue of its location or its state, or you might define it chemically by virtue of its composition, or you might define it biologically. So the atmosphere can be a component of a biogeochemical cycle. Inorganically bound nutrients can be a component. Plants can be a component. And often when you're starting to think about biogeochemical cycles, people like to try and use steady state arguments on the grounds that you have some sort of quasi-equilibrium such that the amount of whatever coming in is balanced by the amount of whatever going out again. And phraseology you will come across are, people will say at equilibrium, which from a chemist's perspective is not true. You do not know that this particular component is at equilibrium in the thermodynamic sense, where the equilibrium is instantaneously reversible, or a phrase you'll often find in dynamic equilibrium, which I can live with rather better. And what tends to happen when you're looking at any environmental system is that when you perturb it in some way, it will simply readjust and find a new quasi-equilibrium condition. But the rate at which it responds can vary hugely. So, for example, if you do something that affects the nutrient status of a soil, you'll see effects on plants growing in that soil very quickly, within a day or two, sometimes. If you do something that changes the nature of soil organic matter, the processes that influence soil organic matter and control its behaviour are much, much slower. So you'll typically see, if you perturb that, it'll take you hundreds to thousands of years for that change to work its way through that component of the system. So here's an example. It's one that's all over the newspapers periodically, and generally grossly misrepresented. So let's look at this. This is a very simple representation of the global carbon cycle. So we have the atmosphere, the gas phase, and the numbers are the number of moles of carbon present in that component. So you've got a lot of carbon in the atmosphere. That exchanges with living components of the system, which we call the biosphere. And you can see that the biosphere carbon pool is actually about half the size of the atmospheric carbon pool. And the principal exchange processes are photosynthesis, the capture of CO2 by photosynthetic organisms, primarily green plants, which moves carbon this way into the biosphere, and respiration, which is what we do, the conversion of more complex organic molecules into CO2, and they're released back to the atmosphere. And the flux is about 10% of the atmospheric carbon pool per year. And pretty much as much goes this way in photosynthesis as goes that way in respiration. So you might say that the atmosphere-biosphere exchange is approximately in steady state. Now, of course, about 2/3 of the surface of the Earth is actually covered with water, the oceans, and the ocean, we'll see this a bit later, ocean water is at a pH a little bit above neutral, and actually carbon dioxide, which is the predominant form of carbon in the atmosphere, is really relatively soluble. So actually you can dissolve atmospheric carbon into ocean surface water. And conversely, when you stir it up with wind and waves and tides and storms, then you can degas some of that CO2 back into the atmosphere. You also get fluxes of other carbon gases into the atmosphere. And what you can see here is that the dissolution, the flux into the ocean surface through dissolution is greater than the flux back from the ocean surface through degassing. So currently, the ocean surface is actually acting as a net carbon sink with respect to atmospheric CO2. If you just stopped everything else from happening, then every year more carbon would go that way than goes that way. And we've defined the biosphere as a living, a living component. The atmosphere is clearly a gaseous component, physically and chemically defined. The ocean surface is water, so it's got some element of chemical definition in there. It's also on the top, so there's some physical criterion used as well. And that actually, ocean surface water actually sits on top of the vast majority of ocean water and doesn't mix with it. So most ocean water is really quite isolated from the surface, and this is due to density gradients. But nonetheless, you have a degree of mixing of ocean surface water with deep ocean water. And you can see that that mixing moves more carbon down than it brings back up. Note also the size of the deep ocean carbon pool. There's an awful lot of carbon sitting down there. So 50 times the atmospheric inventory, roughly, is sitting in the deep oceans. So the ultimate sink, given this, the ultimate sink for carbon is actually the deep ocean. That's more or less in equilibrium. You get a bit more moving this way, than that. You get more moving this way than that. Eventually, all the carbon should end up in the deep ocean. Now, of course, that doesn't happen in practice because the system is not that well constrained. But this sort of analysis lets you think about what happens when we take the very large quantities of carbon that are locked up in fossil fuels and stick them into the atmosphere. Where is that going to go? And how can you follow them around and see what the new quasi-equilibrium for this system will be? So that framework, thinking about fluxes, sources, sinks, movement, transport, is the approach I really want to take to most of this course. But I'm going to start, or take a step back, and think about the planet that we're currently standing or sitting on the surface of. Now, the Earth is it's what's called a differentiated planet. So that actually means that if you went all the way down into the guts of it, you wouldn't just be going through the same stuff all the way. You'd see chemical changes, you'd see physical changes, and that reflects its history, and it reflects the changing physical and chemical conditions as you go deeper. So where does the story of the Earth start? Well, about 10 billion years after the story of the universe starts, actually, but still about 4.5 billion years ago. The picture very crudely, that is often used to describe the formation of the Earth, is that you have a cloud of gaseous material which starts to coalesce, initially into fairly small lumps. We'll look at some pictures in a minute. And those lumps are called planetesimals, sort of mini planets. And as that condensation process goes on, you eventually create a homogeneous aggregate. So you've taken your gas cloud and you've taken that material and you've condensed it down into a lump. But that lump is compositionally pretty much uniform. And what gives us the planet we have today is that you take that lump, this so-called proto-Earth, and you remelt the whole thing. And that melting process allowed chemical fractionation and physical fractionation to go on, such that you see radical differences in composition and structure between the deepest parts of the Earth and the much shallower parts. So, okay, when I sat through lectures like this, they didn't have things like Hubble Space Telescope imagery, which at least make the prettier slides. So you could look out into space using modern astronomy and look for bits of space where the processes we think went on 4.5 billion years ago are still going on. And you can identify things like this, which is an embryonic solar system. So this is going back. This is something which is in the process of forming a star and its planets, and it's essentially a disk-shaped accumulation of material, and you're starting to see a bit of denser accumulation in the middle, which might in time lead you to a star. You can also spot accretion processes. So you take a cloud and it starts to clump together. Fairly early on, it looks more or less spherical. Later on, you've maybe got a bit more shape to it. In this particular example, it's rather elongated. So that you can look into space and you can see what you think are stars and planets and solar systems following the same path that the Sun and the Earth did 4.5 billion years ago. Coming to the Earth specifically, you start off homogeneous, as I said. Now, as you aggregate things together, that's a pretty violent process. So you'll get substantial kinetic energy involved. And as things stick together, that kinetic energy from collisions is manifest as heat. And if you grow your proto-Earth, you're going to trap significant amounts of that heat within it. So the proto-Earth was hot. And the thinking is that it was hot enough to melt metallic iron. And metallic iron is relatively dense. Most minerals are sort of 2.5 grams per cubic centimetre in density. Iron, from memory, is 6 and a bit. So if you have molten iron, which is drifting its way downwards under gravity towards the middle of the proto-Earth, that is actually releasing significant gravitational potential energy. You're moving heavy stuff down, and that gravitational potential energy is also manifest as heat, which makes the whole thing warm up, so you melt a bit more iron, so it all runs away with you. So what you get is you get a remelting of the whole proto-Earth. You get metallic iron moving in towards the core, and essentially you have a gigantic solvent extraction experiment, because a lot of things that are soluble in molten iron go with it into the core, leaving only relatively small amounts behind. The light stuff, if you like, that floats on the metallic iron tends to be aluminosilicate, and that forms a number of different layers. So this is the picture we have of the Earth. You have a solid iron core right in the interior because of the extreme pressure. You've got a liquid iron core around that. Then you move into zones which are dominated by oxides phases. So we have the mantle is next, and we'll split that into the lower mantle and transition zone. I've lost the upper mantle. Okay, asthenosphere. The lithosphere is the top layer, and the crust sits on that, which is a little bit thicker, some tens of kilometres thick in continental areas, and a few kilometres thick in ocean areas. So we can look at that in a little more detail. The core, so this is sort of distances out from the very middle. The inner core, solid nickel iron. The outer core, molten nickel iron. The mantle, as I said, predominantly oxides, but because you change the temperature and pressure conditions there, so the phases which are stable also change. So the deepest layers, it's primarily fairly simple oxide phases. Coming out a bit, you then move into a region where these so-called spinel minerals, which are mixed metal oxides, tend to be stable. And then out again, you're into a region where silicate minerals, like that, tend to be stable. We'll meet that one again. And that top layer of the mantle, which is sometimes called the asthenosphere, is a bit molten, not sort of pour it out of a jug molten, but capable of slow, viscous flow. And then the lithosphere, sitting on top of all that, is dominated by these elements, and as I said, continental crust is a few tens of K thick, is mainly composed of rocks that are high in silica content. Oceanic crust is thinner and is mainly composed of rocks which are lower in silica content. And we'll look at the significance of all that in the next lecture and a half. Okay, so we've seen this sort of picture before. I said that the remelting of the Earth and its differentiation was almost a sort of gigantic solvent extraction experiment. And this illustrates it quite well. So on the left you have the planetary abundance of the different elements. And you can see that the Earth as a whole is an iron, oxygen, silicon, magnesium planet. But then you look at the Earth's crust, so that's the very top of the floaty bit in your solvent extraction experiment, and it's an oxygen, silicon, aluminium, iron crust. So the vast majority of the iron and magnesium has gone down, and proportionately we see aluminium becoming and silicon becoming more important in the crust. So the crust is chemically quite distinct compared with the bulk kernel. And you'll come across this, I'm sure, but just in case you haven't, and so you get the terminology right, you'll have a look. I said that the upper layer of the mantle, the asthenosphere, is a bit molten and you can move things around. There's still a lot of heat in the Earth. You know, if you see pictures of people in South African gold mines, which can be maybe a couple of thousand meters deep, they're all shirts off, sweating like pigs because it's hot down there. And that is heat that's been hanging around for a long time, or it's heat that's generated by radioactive decay in the deep Earth. And that heat very slowly moves towards the surface. And the Earth is a pretty rubbish conductor of heat, so that process is very slow. And when that heat gets to this partially molten upper layer of the mantle, it drives convection currents. And the idea is that sitting on those convection currents, we have the lithospheric plates, a bit like, I don't know, sort of the individual bits of armour of a Roman legionary or something, so that you've got these slabs, but they can all move around relative to one another, driven by the convective circulation underneath. And if you've got these various plates moving around the surface of the Earth, you can think of three different ways in which the plate boundaries can interact. You can either have the head-on collision, a so-called convergent boundary. You can have a boundary where actually the two plates are moving apart, so that's a divergent boundary. Or you can have the boundary where the two are moving or scraping along one another, a so-called transverse boundary. And you can relate these so-called plate tectonic processes to a lot of the big features you see on the Earth's surface. Where do you find mountains? Where do you find volcanoes of particular types? Where do you find deep earthquakes? Where do you find shallow earthquakes? Where do you find high heat fluxes? All of those phenomena relate to what's going on at plate boundaries. So there's a cartoon, very simple. It's sure as hell don't look like that. You've got this movement of heat, you've got convective flow across the surface, you're dragging around the lithospheric plates, which are then bumping into each other. And here are some of the features that you find at different types of plate boundaries. So where you've got divergent boundaries, one of the things you find is a lot of heat. And that sort of makes sense, because if you think the boundary's moving apart, it's going to be pretty thin, it's pretty easy to bring heat up from depth. You find earthquakes at divergent boundaries, but they tend to be fairly shallow. They'll occur within about 100 kilometers of the surface. You'll find volcanic activity as well, and particularly volcanic activity which produces these basaltic rocks. We'll talk more about rocks in the next lecture, But you may recall from a couple of slides ago, basaltic rocks tend to be low in silica content. And these sorts of boundaries tend to be associated with mid-ocean ridges. And you find that the rate at which the plates are moving apart, it may be a few centimetres a year, maybe up to about 20. And these sorts of things you find Japan, Hawaii, Iceland, classical examples of the sorts of features you find around divergent plate boundaries. Convergent boundaries, so that's the head-on collision. You see a lot of earthquakes again, but they tend to be deeper seated than the earthquakes associated with mid-ocean ridges and divergence. You find big geographical features. Where do you find your big mountain ranges? You find it where you've got two plates coming together. And we find volcanic activity there. But those volcanoes don't produce low silica basalts of divergent boundaries. They produce higher silica lavas, rocks called andesites or rhyolites. And again, we'll look at those next lecture. So they've got more silica in than the rocks than the volcanoes associated with divergent boundaries produce. And transverse boundaries, the scraping past one another, tends to be shallow earthquake activity and sometimes a bit of volcanic activity. And here we have a cartoon with absolutely everything, all in one picture. So we start with a divergent boundary there. So that typically will be a mid-ocean ridge, and you've got movement of the two plate edges, one's going that way, one's going that way. What else have we got? Okay, so underneath we've got the convection currents are coming up, and one's pulling this lithospheric plate this way, and one's pulling this lithospheric plate this way. This bit plate is moving that way and meeting another lithospheric plate, which is here. So here we have a convergent plate boundary. And what you typically find there is that one plate will ride up over the other. So one of them gets driven down to depth, so-called subduction. And that can be pushed down a long way. You get material scraped off the subducting plate and bulldozed up into great big heaps, and that gives you mountains. The plate that subducts goes down here. It's getting squeezed, it's getting hot. It's wet because it's ocean floor. Water at high temperature and pressure is an extremely aggressive solvent. So what actually happens is that you start to partially melt and dissolve material out of the subducting plate, and it then effectively, it's partly buoyant because it's light, and it's partly quite corrosive, so it then works its way up, and that molten rock is called magma. It finds its way all the way up to the surface, and we've got some little cartoon volcanoes here. So the basaltic volcanism is associated with these mid-ocean ridges. The volcanism here associated with convergent boundaries, as I said, tends to be higher in silica content because the material is derived from the subducting plate and whatever the magma has risen up through. Okay, so what makes up the Earth? Some facts and figures. We talk about the hydrosphere. There's a lot of jargon. We've had the atmosphere, which is the air. We had the biosphere, which is the living bit. Now we've got the hydrosphere, which is the wet bit. So what is the hydrosphere? It's the oceans, it's the shallow seas, lakes, rivers, groundwaters, and glaciers. We know what the total volume of water is, and the first thing is that the vast majority of water on Earth is salty. Almost all of it is either seawater or seawater that's trapped in sediments. Fresh water is really a very small part of the total water inventory, and much of the fresh water is actually trapped in as ice. Seawater is salty, statement to the bleeding obvious, but really quite salty. All those things in it. Oceans, there's a lot of them. 70% of the Earth's surface, 3.8 kilometres deep. So there's an awful lot of seawater out there. And the atmosphere, we met it earlier on, but a little bit about. Have you done this with Andrew? Yes, no? You probably will in a bit. I mean, I'm only going to do token atmosphere. So what is the atmosphere? Composition is mostly nitrogen, chunk of oxygen, and bits of other stuff. And although the amount of them changes because pressure falls with altitude, the mix doesn't really change up until beyond 100 kilometres. And actually the atmosphere has some structure, which is illustrated here. You can monitor the temperature gradient. You're used to the idea of as you go up it gets colder. Well, that's true up to a point. It's true up to about 10 kilometres. And then you find that it switches over. And if you go beyond 10 kilometres altitude, then it starts to get hot again. So the temperature gradient is negative for the first bit, and that's called the troposphere. Then you hit the tropopoles, the boundary between the troposphere and the next bit up, which is the stratosphere, where temperature rises without increasing altitude. And then you switch over again to decreasing temperature gradient, and finally again to an increasing temperature gradient. So you've got the troposphere, stratosphere, mesosphere, thermosphere, so-called. You get a steady decrease in pressure. So this is pressure relative to pressure at the surface of the Earth. You can see that it falls off all the way up to about 100 kilometres. Note, however, this is a logarithmic axis, so it's not a linear decrease in pressure. And average molecular weight stays the same to above 100 kilometres and then starts to drop off a bit. I really only include that for completeness. That's a picture of the Earth and the Sun. Am I going to do this? No, I'm not going to do this. I'm going to stop here and we'll resume next week and we'll talk a bit about how solar radiation interacts with the atmosphere, but I'm not going to get through it in what's left today. Okay, thank you very much.